use microscale and spectrum. With over 160 journals outputs and 5 books. These editorial linear and multilinear algebra objectives. A fellow of Canadian Mathematical Society and former president of the International Linear Algebra Society. He serves on multiple editorial boards and scientific councils. Please start direction in welcome Dr. Stephen C. Over to you.
Good introduction. Can everybody hear me okay? Okay. So I'm just going to give you a sort of overview of what my plan is for this morning. So I think I have 2 lecture slots. So the first one is going to be a very general and I hope gentle introduction to the topic of perfect state transfer. My idea there is just to sort of introduce you to what are the main considerations, what are the problems that people care about, and then what are the techniques that they're using to try to solve these problems. Okay, so that's the first part. The second part will be, I don't know how to put this nicely, it will be a less gentle introduction to the topic, so buckle up. It'll be more research focused, a little bit more technical in its approach. Again, my expectation and aspiration is not that you will understand everything that I say, but rather that you'll have an understanding of what are the broad techniques that people are using and what are the problems that people are interested in. So I hope that makes sense. And we have lots of time, so if there are questions or concerns that come up, just please don't hesitate to raise your hand. Okay, so I'm going to describe. I'm going to start by talking about something I don't know anything about, and that is quantum communication. Okay, what I promise I'll get to is the idea that quantum communication presents us with an opportunity to work with matrices and graphs to solve problems that are interesting and important. So I'm not going to go into any of the physics, that you understand it, but I will use physics for that motivation. Okay, so we're going to talk about a model for quantum communication that dates back at least 2003. And so the idea here is we're thinking that we're building a quantum computer. Okay, so maybe that's real, maybe that's not real. One of the things that you would like to do inside of any computer is you'd like to be able to transfer information accurately from one part of the computer to the other. All right, and if we're doing it in a quantum setting, then we would like to use the effects of quantum dynamics to help us do that information transfer. So that's the setup. And so Bose describes this idea, what he calls a quantum wire for transferring information, and he's proposing it as essentially a data bus inside a quantum computer. Right? So that's the idea. So imagine we have a qubit, so that's a piece of quantum information, and we want to send it from Alice to Bob. Okay, so here's Alice over here, A. Here's Bob over there at B. And we want to use that quantum effects to do so. And so what we imagine is we have these spins. That's what these little dots are. Okay. And they're entangled. Okay, and that's a complicated physical notion. But the idea is when they're entangled, there's possibility of communicating quantum information from one of the spins to the other if they're entangled. Okay, so let's try and model this mathematically with something way more familiar. So imagine that we have an undirected graph on n vertices. Okay, so that's familiar, right? The little circles here, those are my vertices, and they're going to represent spins. And we have edges that can connect the spins, provided that those two spins are entangled or interacting with each other. And so these little lines here are representing the fact that the spins are entangled. Right? And so what you're seeing here then, it's not a particularly good drawing, but you know what it is. It's a path on N versus yes. Okay, so we think about our spins lined up in a line, and each one is entangled with its neighbors. We want to send quantum information from the left-hand side where Alice has it, all the way over to the right-hand side for Bob. Okay, that's the idea. So we select two vertices, a sender, vertex S, for Alice in our case, and a receiver, that's vertex R, that's Bob. And so what we input the quantum state at the center vertex. We have these physical couplings, these entangled qubits, and they can be made to interact with each other. And what happens is we set it up, and then we just let it go for a period of time t. Okay, don't do anything, right? Excuse me. After a period of time t elapses, the unknown state is communicated to our receiver vertex block in this case, and it's read out, and it is, we hope, close to the initial state we put in the first place. Okay, so that's the general idea. You start with a piece of information, you put it into your spin network, that's what this is, read it out at some time t later, and what you're wanting to do is set up conditions under which the information that comes out at the end of the experiment is either close to or equal to information at the beginning. Okay, that's the setup. Okay, so here's the issue. We're talking about a quantum world, and so that means that there's a bunch of randomness that's involved in communication, and the qubit may not be communicated perfectly between our sender state, Alice in our case, and our receiver state. And so the question is, if we're not sure whether we're going to get good quality communication from one to the other, how are we going to measure that quality? You need some metric to decide whether we did a good job or not. Okay, so the quality, back here, the quality is measured by what's called fidelity. Okay, that's a number between 0 and 1. In fact, it's a function of time t. So the fidelity at time t, which is that t measures the similarity between the information that we put in at the beginning and the information that we read out at time t. Okay, and so what's the ideal situation? The ideal situation is f of t is equal to 1. So that corresponds to precise, exact communication of state. All right, and worst possible case is the opposite. Worst possible case is that f of t is close to 0, and that means that we have not done a good job. I'm going to come back to this fidelity function later on and make it mathematically precise. And so what we're trying to do then is we want to set up a system of the type that I described, where we have these spins and they're interacting with each other, right? We want to let it evolve in time t, and then we want to read out. And I'll say that, so this is one of the physics parts that I don't understand very well. But essentially, what we're saying is, so uniform coupling, that means that all of the interaction strengths are equal between the qubits that are interacting. Unmodulated, that means we don't try to manipulate the system at any point between time 0 and time t. We should just set it up, let the thing evolve, and read out. And XX Hamiltonian, that describes the type of dynamics, quantum dynamics that are involved. Then the dynamics of the communication are described by what's called a continuous time quantum walk on a graph models network. So I'll make a little comment here. So the phrase quantum walk is really supposed to remind you of a random walk on a graph. Many of you who study Markov chains will have met that idea. Except that it's nothing like a random walk on a graph. Okay, we're in a quantum world. The behavior is very, very different than what we would see with the corresponding Markov chain. Nevertheless, that's the phrase we've got to work with. And so I've sort of said this already. We've got this quantum spin network, so we have those spins, some of them are interacting, some of them are not. Okay, we're going to model this as an undirected graph. Okay, the vertices represent spins, and I have two vertices adjacent in our graph, exactly in the case that the corresponding spins are entangled. Right? And so I'm going to think about, learned all about this yesterday, you probably been learning about this growth workshop. I'm going to think about the adjacency matrix of the graph. Okay, so what is that? So that's the matrix that I get that has the same number of rows and columns as the number of vertices in the graph. And I'm going to put a 1 in position PQ if vertex P is adjacent to vertex Q, and I'm going to put a 0 if they're not adjacent. Okay, and so that's a simple way of capturing the information that's in our spin network. And so I just let the system evolve to time t naught, and then I'm going to read out at time t naught. Okay, so I'm so grateful that there's a blackboard here because I wrote the title already. So let me explain what I'm trying to say here. Okay, so first of all, we should move equal sign between bracket and the exponential. I mean, maybe before I go any further with that, I'll just wrap up this paragraph, and then I'm just going to take a little digression here on what this means. Okay, so I've got this matrix U of t, right, and I've written it as e to the I times t times a. Okay, so who's who? Okay, so a is our adjacency matrix. Okay, t is a scalar. It represents time, and I gave the square root of minus 2. Okay, so I did something weird here. Taking the adjacency matrix, I'm multiplying it by the complex unit I times t, and then I'm taking the matrix exponential of that. And so if we're starting at vertex S at time 0, then at time t, system is represented by this u of t multiplied by E sub of S here. So that's my notation for the standard unit basis vector that has a 1 in position S and zeros everywhere else. Okay. All right. So the E sub S that represents our standard state. And what we're hoping is that when I read out of time t naught, what I'll get is E sub R. Okay, so that's a vector that's got a 1 in position R, and zeros everywhere else, times some complex number gamma. I don't actually mind which one it is. I just need it to have modulus equal to 1. Okay, so that's the kind of thing that we're looking for. And this will be the situation in which there's good communication of the state from the center vertex to the receiver vertex. All right. So I'm going to pause here for a second because there's something here I need to unpack a little bit. All right, I would like to talk a little bit about e to the I t a. What on earth do I mean by that? Okay, you all know if I sort of have a number, I do e to the I t times the number, you know what that is. So we're well acquainted with the exponential function for scalars, but the question, this is not a scalar. Okay, this is a matrix, and somehow I am performing the exponential of this matrix. So I just want to tell you, you don't do a lot of matrix analysis in your day-to-day life. I just want to tell you what I mean by this. Maybe I'll just say, for any square matrix. Now, exponential of m, I'm going to define as a power series. Okay, the power series you will at least recognize by analogy with your power series for the exponential function of an ordinary number. So it's going to be sum equal 0 to infinity n to the j. I'll have 1 over k factorial. That's what I mean by the matrix exponential. And I'll just say, it's nice enough to just write it down on the blackboard. There's a little bit of thought you need to put into this, okay? We got a power series. The first thing that we have to care about is, does the power series converge? Right? And there's a little bit of matrix analysis to be done when we're thinking about that. I will go into the mathematical details, but I'll just say we should think about conversion of series. Okay, turns out it always converges, no matter which matrix you're talking about, that's the good news. But there's a little bit of analysis to be done through to make sure that it really does what we want it to. Okay, so I've got this matrix here of T, written as a matrix exponential involving the time parameter and my adjacency matrix. And so I think what I want to do is let's do a little example to try and get some understanding of how this stuff works. All right. And I'm a little bit embarrassed, okay? I'm going to tell you in great detail, excuse me, about what happens when we talk about the graph on two vertices. There's an edge between them. Okay, so I've written it as P2, path from two vertices, so I'll say it's K2, the path from two vertices. Okay, I'm embarrassed again because this is really small. On the other hand, if I can't make it work for this situation, I probably should get out of the business right now. All right, so here's our adjacency matrix. We've got two vertices identified by indices 1 and 2. They're adjacent to each other, and so I have the ones in the opposing off diagonal positions and the zeros on the diagonal. Okay, and here's some great news. If I square this guy, a square, well, that's just the identity matrix. Okay, and so what that means is all the even powers of the matrix A are the identity matrix, and all the odd powers of the matrix A just give me A back again. Okay, and so there's a tremendous amount of simplification that happens there. And so, okay, well, let's go through it. So here's my easy ITA, so it's my U of T written over here. And then, as promised, I wrote it out as a power series to the matrix A. And now I'm going to split it into two chunks. So this is the sum over the even case. And here's the sum over the odd case. Right? And then I use the fact that, well, all these H to the two J's, they're just the identity matrix. And all of the A to the two J plus ones, they're just A back again. Okay, and so that means then that the whole sum, this whole sum here, collapses to something much simpler. I'll just get the cosine of T times the identity plus I times sine of T times A itself. Okay, when it's all done, I do the entire summation. And now, here's to me kind of amazing. Let's choose the value T naught equals pi over 2. Okay, and I want to lift that e to the I of T naught times E1. So E1 has 1 in the first position and 0 in the second position. Okay. Just push through the algebra, and what you find out is that this is the complex unit I times E2. E2 has a 0 in the first spot and 1 in the second spot. Okay, and so that is exactly what we wanted. We started off our system in E1. We let it evolve for a time period equal to pi over 2, and we landed upon a scalar multiple of E2. That's exactly the kind of thing that we're looking All right. And so in this situation, this is an example of what we call perfect state transfer. And so we would say this, that there's perfect state transfer from vertex one to vertex two at time t naught equals pi over two. Just using the language that I've tried to introduce. Okay, great. So now we have one living example, kind of thing we're looking for. Let's try to soup it up a little bit. Now I'm going to look at the path on three vertices. Okay, that's P3. Right, and if I label the vertices appropriately, I've got this guy here as my adjacency matrix. So vertex one is adjacent to vertex two is adjacent to vertex two. Okay. Now go ahead and do the same sort of thing. It's a little more complicated here than in the example that I just did with P2, but we still get lucky. So A squared is this guy I'm going to call B. So it's got a 1, 0, 1 in the first and third row, and a 0, 2, 0 in the second row. And it turns out that when we go ahead and do that, A cubed is 2 times A. Okay. This is giving the lecture. Okay, so I was in the middle of telling you about the path of reversibilities. Here's our adjacency matrix. I square it, I get this magic matrix B here. And what's useful in this context here is if I cube the matrix A, I just generate 2 times A dot B. Okay, and so what that means is that we get a similar sort of setup that we saw with P2. Okay, that if I look at the 2j power of the matrix A, that's just a scalar 2 to the j minus 1 times B. And if I look at the 2 to the j plus first power of the matrix A, that's just 2 to the j times A. And then I just do the same trick as before. I'm going to split up my power series expression for the exponential of e to the I t times A. Okay, and I'll collect up a bunch of terms. And when it all shakes down to the end, e to the I t A is the identity matrix plus the cosine of the square root of 2 minus 1 on top of 2 times B plus I times the sine of root 2 over, sine of root 2 t divided by root 2 times A. Okay? So that's just a bunch of algebra that we work out. And so in particular, if I pick the time t naught equals pi divided by the square root of 2, then a whole bunch of miraculous cancellation appears, and I just get this guy here. So it's just essentially minus the back identity matrix, minus the matrix that has 1 for the back diagonal. And in particular, what do we see here? Imagine that I apply this matrix to the vector E1. Well, when I do that, I just pick out the first column of this matrix here. So I get minus E3, and that's exactly the kind of setting we were looking for. So in this situation, there's perfect state transfer from vertex 1 to vertex 3 at time pi over the square root of 2. Okay, good. Now, I have to apologize for the music that came before. I had actually wanted to come in just now to have a sort of celebratory moment for this perfect state transfer. So, okay, it's 11.5-hour time difference between where I am in Canada and where I am here, so that's probably part of it. Okay, so now I have 2 living examples, P2 and P3, in which we have this desirable thing, this perfect state transfer from one vertex to the other. So that's good news in some sense. At least we're talking about something where it's actually realized. Where the issue here is these are very small examples, okay, in terms of the number of places involved. Please.
So you are choosing the time very delicate. Obtaining such type of matrix.
Correct.
What does I apply even terms of 0, 1 times that?
Yeah, so other times are going to give me different phenomena when I see the readout here. And so, so you're absolutely right. The time is chosen very deliberately. And what we see is there's only going to be certain very special times that we're going to be able to achieve this perfect state transfer. Okay.
You will not call it perfect state transfer if you get linear combination of.
Now, and something else that's also of terrific interest is called fractional revival. I will not talk about it today, but if you want to talk offline with me about it, we can certainly talk about that. So everybody understands the question. Question was, do I care about maybe not necessarily just generating one of these unit vectors, but a linear combination of the 2 of them? That's also an interesting problem with quantum information theory. Okay, but not what we're going to talk about today. All right. So I want to formalize now and make good on some of the promises that I made to you earlier, and also generalize a little bit too. So now we're just going to take some undirected graph on vertices from 1 to n. I don't think I wrote it onto the slide here. You might as well assume that the graph is connected. Okay, that's kind of the only interesting case. You can imagine if the graph is disconnected, there's no possible way to send information from one component to the other. Okay. So here's my famous matrix U of T in the Iclaa. And now let's just sort of step back and examine it a little bit. It's a matrix with complex entries in general. It is symmetric, okay, not Hermitian, symmetric. In other words, the entries in the JK position and the KJ position are equal to each other. Right, and it also happens to be a unitary matrix. So if I take the conjugate transpose of U times U back again, I get the identity. Okay, and so in particular, let's look at the unitary part. What that means is that for each choice of J equal 1 up to n, if I look at this expression here, so I go into my unitary matrix U of T. I select out the entry row J column K. I take its complex modulus and I square it. Okay, so I take all those guys and I sum them from K equals 1 up to n. Okay, that sum is equal to 1 for every possible choice T. Okay, I'm just using the fact that these units here. Okay, and so what do I have here? So these quantities for each T, the quantities U of T in a position JK modulus squared. So that's a bunch of non-negative numbers that add up to 1. In other words, they form a probability distribution. And so what we then say is we're going to take this guy here. The interpretation is that's the probability, continuous time quantum walk that starts at vertex J, arrives at vertex K at time T. Right? And this is this fidelity of state transfer that I was telling you about. Okay, when the fidelity here is 1, that says that the probability that we start at J and arrive at K at time T is equal to 1. That is perfect communication of our state. All right. So that's just what I said here. There's perfect state transfer from JK at time T naught. If this expression here, U of T naught, that has in its JK position a complex number whose modulus is equal to 1. Right? Here's another way of saying the same thing. It's pretty so imagine what happens. Imagine I've got a 1 in position JK in this U matrix. Right, well, that means that all of the other entries in the same row and in that same column must also be 0. Okay? And so that's the same as saying that if I take U of T naught and multiply it onto the standard with the basis vector E sub j, that is some complex number gamma times E sub k, where the modulus of a complex number is 1. And I'll just go. We can just go through a little exercise here. I'm talking about the perfect state transfer from J to K, but observe that it goes the other way as well. Okay, imagine I have perfect state transfer from J to K. So U of T naught times Ej is gamma times Ek. And now I'm going to go into that whole equation, and I'm going to take the complex conjugate of everything in sight. Right? So what's the complex conjugate? Well, that's for the matrix U. That's EU, that's U of minus T naught times E to the J. That's gamma bar E sub K. Now I just multiply from the left by U of T naught and from the right by gamma. And I recover the fact that U of T naught times EK is gamma EJ. Right? And so one thing in particular I observe from that is if there's perfect state transfer from J to K, then automatically there is perfect state transfer from K back to J. Right? So there's a reciprocity there. And another interesting thing, excuse me, to find out. If I look now at twice the readout time, so U of 2 T naught times E sub J. That's just gamma times U naught times EK. Now I just use this back here, that's gamma squared times E sub j. And so, up to the complex number gamma squared, that has modulus 1. I start with Ej, and after time 2t naught, I land back at Ej again. Okay, that's known as periodicity. Okay. So that's the setup, so what I want to do now is talk a little bit about some of the mechanical stuff that we have to do, right? I told you, it's gone now, but I gave you my expression. I gave you my expression for u of t, right? This exponential as a power series, but I want to think about it in a slightly different way. And I hope this, when we put it together, you'll start to see how the techniques of spectral graph theory are going to be important in our study of Lorentzian transform. Okay, so I'm just going to back up. Let's take any n by n real symmetric matrix. So n equals n transpose and all of these. Okay. And so let's write out its distinct eigenvalues as lambda 1 through lambda k. And then I can write this matrix n in terms of what we call the orthogonal eigenprojection indices associated with the eigenspaces. So I'll set it up like this. So matrix n is a linear combination of these matrices E sub j. Summation runs from 1 to k, and the scalar lambda j is what multiplies onto E sub j. And now let's just talk about these E sub j's for a second because they're important. Each E sub j is symmetric. If I square it, I recover E sub j back again. If I take two different ones, EJ1 and EJ2, and I multiply them together, different indices J1 and J2, I get the zero matrix. So there's a sort of orthogonal diagonality condition. And the last is that the sum of the EJs is the identity matrix. Okay, so I want to, if you've never met this thing before, it's maybe a little bit mysterious, but what I want to do is try to unpack it a little bit and convince you that it's actually something you already know. All right, so, how would I construct these E sub j's? Okay, so what I'm going to do is I'm going to fix an index j, and I'm going to think about an eigenspace that corresponds to lambda j. Right, so that's some, if my matrix is n by n, then the eigenspace corresponds to lambda j, that's some subspace of R n. And let's suppose it has dimension d. All right, so it's a subspace, so it has a basis. And if I didn't like the basis that I started with, I can do a Gram-Schmidt orthonormalization, and I can produce an orthonormal basis of that subspace. We can always do that. All right, and so let's do it. So I'll let the vectors x1 to xd. Let's have them be an orthonormal basis of our eigenspace of n corresponding to the eigenvalue lambda j. And now what I'm going to do, I'm going to build this matrix E sub j in front of you by doing the following thing. I'll take x sub L, so that's the L vector in my orthonormal basis. I'm going to multiply it by x sub L transpose, and then I'm going to add those guys up as I run the vector summation from 1 up to t. Okay. And now I'll just say we can then check that the E sub j's constructed have the desired properties. And maybe let's just let's go through it a little bit. So does everybody agree that if I build E sub j like this, that it is symmetric? Sure it is. Right? It's a sum of things, it's a sum of rank 1 symmetric matrices. Yes? Okay. EJ squared is EJ. Okay, let's just think about how I would compute EJ squared. Well, I'm going to take this summation here and square it. I'll have a whole bunch of products of the type XL1 transpose times XL2. All right, But the XLs will orthonormal. So if L1 and L2 are different from each other, that number is 0. And if they're the same as each other, that number is 1. Okay, and so that gives me that the square of ej is just ej back again. Okay, now let's take a look at the E sub j1 times E sub j2 for different indices j1 and j2. Okay, I'm going to have two sums multiplying each other. Okay, and so I'll have a whole bunch of products that look like x sub l, where that came from the J1 eigenspace, and x sub l hat, where that came from the J2 eigenspace, and I'm looking at an inner product of those two guys. But we remember from our whatever first or second linear algebra class that for symmetric matrices, if I take an eigenvector from one eigenspace and an eigenvector from another eigenspace, they're automatically orthogonal to each other. Okay, and so that says that different E matrices, EJ1 and EJ2, I take the product, I'm going to get the zero matrix. Okay. What is this last condition here? This is essentially telling us that when I add up all of the EJs, I get the identity matrix. So another way of saying that is that somehow the eigenspaces corresponding to a symmetric matrix generate the entire space bargain. Okay. So it's a little bit hand-wavy, but I hope you get the main idea. And as I said, what I'm using here to generate these eigenprojection matrices is nothing more than what we would have learned in our first or second class. All right. Right, now I want to put these things to work. So let's do the special case of interest to us. We're going to talk about the adjacency matrix of our graph. I'll have our distinct eigenvalues, lambda 1 to lambda k, and then we're going to have these eigenprojection matrices E sub j. Oh, maybe before I run on, let me just say one more thing about these E sub j's. If you like to think of things more geometrically, what you can think of is E sub j is the matrix that corresponds to the operator that takes the vertex, takes the vector z, maps it to its projection in the corresponding eigenspace that goes with lambda j. It's another way of seeing the thing. Okay, so it's sort of a natural interpretation of EJs as projection matrices. Yeah, please. Yes.
Can you select the columns corresponding to our regular?
Yes, lovely. Exactly right. And in fact, the description that I gave you in terms of these other products and orthonormal eigenvectors is another way of saying just what you told me, Rick. And so, yeah, so another way of thinking about these EJs is just take a look at the basic, what is this, eigen decomposition for our symmetric matrix, and you write it out in the slide reading. Thank you. Okay. So I'm keeping my setup here. I've got my lambda j's, got my EJs, and observe a great thing happens when I take powers of my matrix A. Okay, and again, you can just do this one in your head. I've got this big sum, it's a linear combination of these EJs, and now I power it up. So that's going to be that sum powered up. But remember that the if I take any product of the type EJ1 and EJ2, J1 and J2 are different from each other, that's going to cancel out and get me 0. And when I'm done, what I learn is that the Lth power of the matrix A, this guy here, is the same as what I would get if I keep my E sub j's, but I now I multiply them by lambda j raised to the Lth power, sum from j plus 1 on j. Okay, so it greatly simplifies the kind of computations we're going to do when we go and look at our matrix exponential e to the I to the k. Okay, now I'm just going to write it out. Okay, this is the formula I wrote on the blackboard, and then I erased that when that showed up. Okay, and now I'm going to say, well, here's my new expression for a to the L. It's this guy here, just from this formula here. And now what I notice is, well, what's dependent on L here? The EJs are staying as they are. The only thing that's being affected by the powering operation is the lambda J's. So I'm just going to collect up the terms a slightly different way. Okay, so I'll capture L equals 0 to infinity, IT to L factorial at the bottom, lambda J to the L, all multiplying onto E sub J, that's something J equals 1 to K. And then this you recognize as the scalar exponential e to the IT lambda J. Okay, so that's a very long-winded way of saying, if I already have these orthogonal matrices E1 through EK in hand, computing the matrix exponential is actually a snap. All I do is exponentiate the corresponding powers, the corresponding eigenvalues multiplied by I times T. Okay, good. So, as I said, there's a deep connection here between the spectral graph theory, because I'm talking about eigenvalues and eigenvectors, and this perfect state transform. Okay, so I'm going to revisit my P3 example and in a slightly different way. So here's my matrix A. It's not so hard to figure out that the eigenvalues of A are plus minus the square root of 2 and 0. And then here's the eigenprojection matrices that go with them. I just worked it out on paper and we did the LaTeX version. So here's E1. This subscript here just reminds me of which eigenvalue that goes with square root of 2. Here's E2 going with the square root of minus the square root of 2. And then here's E3 that goes with 0. Right? I just crank out my expression for e to the ITA like that. Okay, and if you don't like the sound of my voice for the next 5 minutes, you can just verify that this expression here is the same as what I gave you on the slide, with these slides. Okay, so it's straightforward computation. Okay, by the way, you might have been a little bit mystified by the appearance of pi over the square root of 2 when I was looking at that beta time in my earlier visit to this example, but maybe this bit here gives you the sense that, oh, actually that was the right choice to make somehow. Something about the square root of 2 is part of this. Okay, so I'm just saying here, we're revisiting our example, but now through the lens of these orthogonal behaviors. Okay, and so I want to start making my way back from the eigenprojection matrices towards the state transfer, where I'm going to apply these ideas to see what we can get. Okay, so imagine I've got our adjacency matrix A, and we have perfect state transfer from A to E times T1. Okay, write out the eigenprojection matrices, here they come. There's U of T, that's B to the ITA. You know how to compute that because we've got these eigenprojection matrices in hand. And so let's look at what happens here. So U of T naught times E sub A, so it's a 1 in the 8th position, and 0 is everywhere else. That gives me gamma times E sub B for some complex gamma. Okay, now let's just work it out here. I'm going to take both sides of this equation here, and I'm going to multiply it by E sub J. All right, so I'll get gamma E sub J times E sub B. That's just E sub J T naught E sub A. And then think about how the E sub J is going to multiply onto U of T naught. It's going to kill everything in that summation except for the E sub J term, not for the B and the only thing that survives. And so I'll get E to the I T naught lambda J E sub J times E sub A. Okay, so that's a lot of letters and numbers up there, but what I want you to take away from that is for each J between 1 and K, right? If I take E sub J and multiply it onto E sub B, that's the scalar multiple of E sub j multiplied onto E sub a. Right. And of course, both those vectors, this one and this one are real, and they're real and they have modulus equal to 1. So that means there's only two choices. Scalar is either 1 or it's minus 1. Okay? And so so for each j between 1 and k, E sub j times b is either plus E sub j times a or it's minus. Okay? It's entirely possible that both those vectors are 0. So when this happens, when I've got a pair of indices A and B, so that this term holds for all possible choices j equals 1 to k, we say that the two vertices are what we call strongly co-spectral. Okay? And if I have such a pair, I'm going to define this guy here, sigma sub AB. So that's all of the eigenvalues lambda j. So that E sub j times EA is a non-zero vector. Okay? Sometimes we call that the support of vertex A. And of course, it's going to be the same because the support of vertex. All right. And so we're going to have we're going to take this set here. So this is all the eigenvalues where the eighth column of E sub j is something interesting. And now I'm going to partition that set into two pieces. The part where the eighth column and the bth column agree with each other. Right? That's when the scalar is 1. And the part where the eighth column and the bth column differ by a factor of -1. All right. So you can think of this as taking the support and partitioning it into a positive part of the support and a negative part of the support. Loosely, that's what it means. All right. So I've got a minute or two for an interesting digression. If you don't like perfect state transfer, but still like graph theories, if you like this thing. Imagine I've got these vertices that are strongly co-spectral. And I can perform the following thought experiment. So I'm going to fix a natural number L. And now I'm going to look at this guy here. So that's EA transpose A to the L times EA. Okay, so let's think about that. What is that really? That's the diagonal entry in the A position, the matrix A to the L. Yep. Okay. And now we're going to go through this long computation to see what happens here. Well, I have A to the L, so I can write out A to the L as the sum lambda j to the L, E sub j, and we hit it with E sub A transpose and E sub A. Okay. We can restrict that summation to eigenvalues that are in the support of vertex A, of course, because the other ones will not contribute anything to the sum here. And so let's do it like that. So here's just rewriting this guy here. I'm using the fact that E sub j is symmetric, and then it squares E sub j back again to that property earlier. So that's another way of rewriting this. And then we will just say, the area is strongly co-spectral. So this E sub j times E sub A is either plus or minus E sub j times E sub B. It's one of those two. Okay. If they're both plus, they're the same. If they're both minus, there's the minus in this one here and this one here. And what I learned from all of that is that this is the same as the sum of the lambda j's in the support, lambda j to the L, EB transpose E to the J, E sub j times E sub B. Okay, reconstruct that all back again. I get the bth diagonal entry of the matrix. So it's a long computation. No step is difficult. But what I learned is for each power of the matrix A, the diagonal entry in the eighth spot is the same as the diagonal entry in the eighth spot. Okay. Now, let's think about the Lth power of the matrix A. when I power up the matrix A, I hope that somebody taught you this earlier in the spectral graph theory bit, but if not, it'll be a little extra exercise for you. The L power of the matrix A counts the walks in graph from one vertex to another, provided that the walk has life. Okay, that's an easy induction proof if you've never done it before. And so in particular on the diagonal, okay, what I'm finding in the outpower of the matrix A on the diagonal is the number of walks of length L from that vertex back to itself. Yeah. What we're saying then here is, if A and B is strongly co-spectral, the number of closed walks, okay, from vertex back to itself that contain vertex A is the same as the number of closed walks that contain vertex. Okay, so I raise all of this because kind of I started this journey of strongly co-spectral, it was entirely algebraic. Right? It was all about these orthogonal eigenprojection matrices and where the columns matched or didn't match by a factor of -1. So the whole thing is only about algebra. What I get as a consequence of all of this is something that is entirely graph theoretic about the number of closed walks involving A that involve. So I'll say that the two notions are different because closed walk condition is not equivalent to the notion of strong co-spectrality, right? But there are lots of examples where one seems to mirror the other. Okay. So what I want to do here is start to creep towards some sort of characterization of perfect state transfer in an algebraic sense. Okay, so imagine we've got our adjacency matrix A, and we have perfect state transfer for A via time T naught. Okay, so that gives us this expression here. The entry U of T naught in row A, column B is a complex number of modulus 1. And of course, A and B is stronger than spectral. And so I'm just going to follow my nose here to try and come up with something interesting here. Will give us a bit of leverage in trying to understand this problem in more technical detail. Okay, so that's just the hypothesis, right? And now U of T naught, I'm just going to write it out exactly the way you predicted I would, because I give you this long harangue about these E sub j's. So we're going to write it out like this. I'll take the sum. Two things, the only things that are going to contribute to the sum are the lambda j's that are in the support of vertex A. I'm going to split that up into a sum over the positive part of the support and a sum over the negative support. Okay? And so let's see what we get when we work through that. Okay, so E sub j EB is the same as E sub j EA on the positive support. Part of the support, and E sub j EB is minus sub j EA, the negative part of the support. Okay, so far so good. I've just taken the taken the modulus of that, and now I'm going to do an elementary inequality, triangle inequality. Okay, so here's less than or equal to, and now I'm just going to push it through. All right, it's less, this is going to be less than or equal to the sum over the positive part of the support of the diagonal entries in the A diagonal entries in E sub j, plus the sum over the negative part of the support. All right, and what is that when I put it all together? Well, that's the number 1, because remember that E sub j's sum to the identity matrix, and so when I take the 8 diagonal entries and sum over the support, I'm going to get the number 1. Okay, good. And so the good news from all of this is it gives us a little clue as to where to go next. Okay, I got the number 1 is equal something or other, less than or equal to equals 1. Okay, so equality holds in the triangle inequality. Right. Now, we can think back to, I don't know when you would have learned this. I usually teach this in linear algebra, but it might have learned it in an analysis class. What is equality hold in the triangle equality? Well, when all the things that you're adding up have the same complex parameters. Okay, that's what equality goals we try and equality. And so what does that mean? That means that there's some complex number z with modulus 1, so that for all of the lambda j's that are in the positive part of the support, e to the it naught lambda j is equal to z. And for all of the lambda j's of the negative part of the support, e to the it naught lambda j is minus z. And that's the only way that we could get equality in a triangle. So what I want you to see here then is asking for perfect state transfer means that we have to ask for something very special to happen. Somehow there's this magic number T naught, so that when I look in the positive part of the support for vertex A, I get Z, and when I look in the negative part, I get A. Something really special has to happen in order for this to take place. Okay, so let me do a quick example here. What do we have here? Well, maybe I'll just sit here. I've got this part here. So our T naught was pi over 2, and we were looking at perfect state transfer from vertex 1 to vertex 3 inside of P3. And so when I look at that, so what do I have? I've got, here's the positive part of the support here. It's the eigenvalues √2 and minus √2. Okay, and when I compute that expression here, I get -1 for e to the it times √2 and e to the it times -√2. The negative part of the support that was the eigenvalue 0, and of course e to the it naught times 0 is 1. Okay, exactly matching up what we expected. Positive support get positive z, and the negative part of the support we get negative. And now I can go through the same sort of exercise here with P4. Wow, look, I got to the last one for vertices. That's pretty amazing. So spoiler alert, this is going to be a bit of a disappointment. Here's the adjacency matrix for P4. Here are the eigenvalues. Just work them all out. Okay, so it's plus or minus 1 plus or minus square root of 5 all the way up to 2. It's not too hard to figure out that vertices 1 and 4 are strong for the spectral. That the positive part of the support looks like this, 1 plus or minus root of 5. And the negative part of the support looks like this, -1 plus or minus square root of 5 multiplied by 2. Now we ask ourselves, you know, the perfect state transfer from vertex 1 to vertex 4. Well, what are we looking for? We need some magical complex number z, modulus 1, so that e to the it naught times 1 plus root 5 on 2 is z, and e to the it naught times minus 1 plus root 5 on 2 is also z. And when I go to the negative part of the support, okay, e to the it naught minus 1 plus root 5 on 2 is negative z, and e to the it naught minus 1 minus root 5 on 2 is also minus z. Okay, again, like the sound of my voice, you can spend the next 2 minutes convincing yourself that this is impossible. There's no way to find a complex number z that satisfies all those conditions. So the conclusion is there's no perfect state transfer P4 from one end vertex to the other. Not possible. Okay. So the disappointment that P4 example. And so what I want to do is now give you a rather long-winded statement of the theorem. Don't worry, I'm not going to prove it. And what I'll say is this is a characterization of perfect state transfer. And what it is essentially taking all of the ideas that I've put in front of you all already and implementing them in a particularly clever way. Right? So this is the work of this Gabriel Cucino thesis. All right. So here's the setup. We've got our connected graph with adjacency matrix A, and we'll take a couple of vertices A and B. Here's the support on A and B. And let's assume with laws of generality that the eigenvalues lambda 1 to lambda k are ordered decreasing. So there's perfect state transfer between A and B if and only if the following conditions hold. First of all, the two matrices have to be strongly cospectral. We saw that condition earlier, that it was an important piece of the puzzle. This really comes out of this notion of vertex periodicity that I told you about before. The elements of the support are either all integers. Oh, that's interesting, because didn't you just have a long session yesterday on graphs with integer eigenvalues? Okay, so they're integer eigenvalues for graphs are cool and useful, it turns out. Okay, so either the elements of the support are all integers, or there are some integers p and q1 through q sub k and a square root integer delta, so that the lambda j's in the support can be written as p plus qj root delta of 2 for each j between 1 and k. And I don't love this convention here. We'll take delta equal to 1 to cover the case that the elements of sigma 8 are all integers. It's a convention in the literature, I don't like that much. Okay, so what do I do? So I've got these eigenvalues of special form, and now I'm going to look at the following collection of expressions. I'll look at lambda 1 minus lambda j divided by the square root of delta for each j between 2 and n. Okay, so that those can be a collection of integers, and I'm going to form their GCD and energy. Okay, so then for each j between 1 and k, we have to have the property that if lambda j is in a positive part of the support, lambda j is the positive part of the support if and only if this lambda 1 minus lambda j over root delta is an even number. Okay, you can think of this as the plus dead thing that I was telling you about earlier, corresponding to the positive part of the support. Or the other possibility, lambda j is the negative part of the support if and only if lambda 1 minus lambda j over delta is odd, corresponds to the minus z condition that we came earlier. All right, when all of this step goes through, the minimum time at which there's perfect state transfer from A to B is T naught given by pi divided by g square root delta. Okay. Again, let me see if I can pick maybe the easiest thing to think about when you're looking at this, to be not surprised by this form, is to think about the case of P3. Okay, the case of P3, we had a square root of 2 in the denominator here. The 2 is serving a role is delta theta. I talked about it. Okay, so that's a long and complicated characterization of perfect state transfer. But as I said earlier, all of the ideas that I gave you earlier, those are the building blocks for this theorem.
While we are talking about if I talk about the vertex AC, are these lambdas, can it happen with the share? Like eigenvalues are different support ratios.
So let's see, true, yeah, true. So I could have different pairs of vertices so that the eigenvalue supports are the same. The easiest example would be take a pair of twin vertices, right? Now take a look at the support with some third vertex. Okay, the twin vertices will share the positive part of support with that third vertex and the negative part of support with that third vertex. Okay, so just a quick note here. Imagine that we have perfect state transfer from A to B and from A to C. So the theorem's off the screen here, but basically one of the takeaways from that big theorem I just gave you is that the conditions for perfect state transfer are all about the support, the eigenvalue support of vertex A. Right? And so what we deduce from that is the minimum perfect state transfer time T naught from A to B, or from A to C only depends on the properties of the eigenvalue support, which in turn only depends on the vertex. Okay? What that means is, if I take that minimum PST time, that minimum state transfer time T naught, multiply U T naught onto EA, that's gamma E, right? And it's also going to be equal to gamma 2 times E sub C, and it follows vertex B has to be the same as vertex C. Okay, in other words, if vertex A is involved in a perfect state transfer with some other vertex, it's only involved with one other vertex. Okay, that's sometimes called monogamy of perfect state transfer. Only one partner. Okay, that's the perfect state transfer.
Then it cannot happen.
If it's perfect. So your question was, could they share the same eigenvalue supports? Yeah, and so they might share the same eigenvalue supports without having perfect state transfer.
But if it is of the state transfer.
Right.
So does it divide the entire these states into some little class?
Yes, so there'll be pairs of states for which there is perfect state transfer, and they'll be separated from each other in some sense, and then there'll be a bunch of states which don't even get perfect state transfer at all. Okay, so I want to give you a couple of constructions just quickly as I wrap up. Because much of what I've said has sort of been kind of bad news, small graphs and some complicated technical thing that we have to try and understand to generate perfect state transfer. So, but I'll run through quickly a nice connection between matrices and certain types of graph products. So I've got a couple of matrices A and B. They're conifer products. So A cross B is just a block matrix that I get by taking the entries in A, right? I use the scalars in the entries of A. I multiply those onto the matrix B, and then the corresponding block matrix. It's a straightforward idea. I have a related idea involving graph products. If I have two graphs, G1 and G2, on vertex sets B1 and B2, their Cartesian product is a graph whose vertex set is on B1 cross B2. That's ordered pairs, one vertex from B1 and the other from B2. Two ordered pairs are adjacent in the Cartesian product. If one of two things holds, either the first guys are the same, x1 is x2 is the same as x2, and the second guys are adjacent in G2, or the other way around, the second guys are the same, and the first guys are adjacent in G1. So that's the Cartesian product. And if I want to build the adjacency matrix of the Cartesian product of G1 and G2, I do it by taking the adjacency matrix for G1, the adjacency matrix for G2, and I build it like this. Okay, involving the conifer product of A1 with the identity matrix plus the conifer product with the second adjacency matrix A2. Okay, so that is the Cartesian product of two graphs. You can find this for any two graphs. And then it's not so hard to show that if I want to look at e to the IT times the adjacency matrix of the Cartesian product of G1 with G2, that's just the conifer product of e to the IT A1 with e to the IT A2. Okay, so that's just a bit of multiplication with block matrices. It's not too hard to work out. And so what's the upshot of that? Imagine I've got two graphs, G1 and G2, and two good pairs of vertices. Okay, I've got perfect state transfer from A1 to B1 in the first graph G1 at time T0, and separately, I have perfect state transfer from A2 to B2 in graph G2 at time T0. Then from this expression here, it turns out there's perfect state transfer from the, in the Cartesian product from the vertex A1, A2 to the vertex B1, B2 at time T0. Good. So what that does then is that gives us a way of taking little graphs that have perfect state transfer and producting them up. I know that's not a phrase, but I'm saying it anyways. Producting them up to get bigger graphs that have perfect state transfer. And so here's an example. Consider the D cube. So what are these guys? These are the vertices, because the graph on two of the D vertices. The vertices are the tuples of zeros and ones, the D tuples of zeros and ones. So the vectors of length D that have are filled up with zeros and ones. And two vertices are adjacent, given only as the corresponding D tuples differ in exactly one spot. There's exactly one position where one of the vectors is a 1, the other guy is a 0. Okay? It turns out for each vertex, there's perfect state transfer at time pi over 2 from the vertex to its corresponding complementary D tuple. And what's the complementary D tuple? It's just the thing you think it is, right? Start with the original tuple and switch all the ones to zeros and all the zeros to ones. Okay. And so why is that the case? Because this D cube, I can write it as the default Cartesian product into itself. Okay, and that's exactly what we saw on the previous slide, right? So P2 gives us perfect state transfer at exactly time pi over 2. I take this default Cartesian product and I get a graph that has perfect state transfer from each vertex to its complementary D tuple. Okay, so there's some good news and some bad news about this family of examples. Okay, so number one, an infinite family of graphs with perfect state transfer. Okay, that's pretty good news. The graphs are sparse, okay, in the sense that there are not very many edges. It's pretty easy to see that the D cube is a regular graph, each vertex has degree T. Okay, so relative to the size of the number of vertices, the graph is sparse. The readout time is short. Okay, that's important. Why? Remember, what were we trying to do? We're trying to communicate information from one spot to the other. Okay, I would like to do it in short time, thank you very much. I don't want to have to wait a long time to be able to transfer the communication or transfer the information accurately. And last is I can realize any diameter through a construction of one of these D cubes. Again, straightforward exercise, the diameter of the D cube is D. No surprise there. Okay, good. This and why is the diameter important? It's a proxy for the physical distance that I'm sending my information from one space to the other. Right? So we'd like to be able to transfer our information in short time to a faraway place. Okay, the disadvantage is that if I want to transmit a qubit a distance of d with perfect state transfer, I need an exponential in d number of vertices for this family of graphs. So the graphs are sparse, but they have a massive number of vertices. So that's the downside to it. Okay. I'll just give you a couple of quick examples. These are results from the literature. The only complete graph with perfect state transfer is K2, stage P2. The only cycle with perfect state transfer is C4, that's the 2Q. So maybe it's not too surprising. This is a very hard result and an important one. The only trees with perfect state transfer are P2 and P3. And kind of a negative result. This is a result of Chris Gottfried. So for each natural number K, there are at most a finite number of graphs of maximum degree K that admit perfect state transfer. So sum up from all of these things, we're thinking the perfect state transfer is a rare phenomenon. And maybe if you think back to that horrible theorem that I presented to you, it's not surprising. We're asking for a lot out of the eigenvalues and the eigenvectors of the matrix in order for us to generate. Okay. So, and so for that reason, people go to a lot of work to try and construct interesting graphs with perfect state transfer because they're hard to find. Here's an example of a construction that seems to work. So I think it says, she talked about the majority of two graphs, G1 and G2. So what do? I just take the union of G1 and G2, and then I add all possible linkages in between them. And so here's an example. Take of a nice construction. Take a k-regular graph on the vertices, and now let's have I'll call this O sub 2. That's the empty graph on two vertices. So it's graph with two vertices and no edges. Okay. So I'm going to build this this magic number delta as k squared plus 8 times n. So k is the degree of regularity of my graph G, and it's the number of vertices. And then if it happens that delta is an integer, and the k and delta are both congruent to 0 on 4, and the largest power of 2 dividing k is different from the largest power of 2 dividing delta, then there's perfect state transfer of the join of the empty graph on two vertices with B between those two vertices that came from the empty graph. Okay, so to me that's kind of interesting, right? G, what did I ask for out of G? I said it needed it to be regular and have some reasonable parameters in terms of the number of vertices and the degree of regularity. I didn't ask for G to have perfect state transfer, didn't ask for that. Okay, and maybe it doesn't, but if I join it up with two more vertices that are not adjacent to each other, then I can generate state transfer. So just as a quick example, you can take k to be 0, okay, so G is the empty graph. So I'm looking at, and so let's take a specific example, the empty graph on 8 vertices. Then the join of the empty graph on 2 vertices with the empty graph on 8 vertices has perfect state transfer, as it turns out at time 5 before. Here's another example. So I can take a Cartesian product of 2 cycles for my G. So one cycle has length 4L minus 2. The other has length 2L plus 1. So then G is a regular graph. Degree of regularity is 4. The delta is 8 times L. And then according to the previous construction, there's perfect state transfer between the degrees of the empty graph on 2 vertices that I used as part of the construction. What's different about this one is this is an example where our graph has both integer and and irrational eigenvalues, unlike many of the previous examples. So, okay, I'm just going to wrap it up. Okay, so perfect state transfer is desirable, and an important thing to study in terms of quantum information theory. I hope that convinced you that if you have a decent grounding in spectral graph theory and algebraic graph theory, then you have a lot of the tools in hand right now. As I mentioned earlier, it's believed to be quite rare. And that said, even though it's rare, there are lots of people who are putting work into trying to generate graphs that have perfect state transfer from one vertex to another. There are a lot of variations on this body of work. We could think not just about adjunctive graphs. We could talk about weighted graphs, because our edges have weights. We could talk about something called almost perfect state transfer. I'm going to talk about that a little bit in my next lecture. We can use different Hamiltonians. So today I talked only about the adjacency matrix. There is an entire theory parallel to this for the Laplacian matrix. Okay, any of the techniques go through, but then there are some slight differences between one and the other. Let's see, we might also think about other types of quantum states, not those that just correspond to a single contextual graph. When we think about something that involves 2 vertices, talk a little bit about that in 1 or 2 days. So I should say there is a lot of work to be done. It's a challenging research area, but it's also important. All right. Sorry, I'm 1 minute over, but I'm going to blame it on the band that interrupted me earlier. Thanks for your attention. believe we have a break until 11:30. Yes? Okay, perfect. Questions? Please. I'm sorry to hear that. That's not very good. Absolutely. Yeah.
So here we are at the question about 16%, or is it not the same?
No, so it's just the burn, so you can think about, let's look at this construction here first, right? So I've got a 5-part 10, or complete 5-part 10 graph, so I've got 2 vertices, 1.10 cent, 8 in the other. It's just the two vertices in the first quartile set. They're the ones that generate, perfect state transfer, and there's basically no information about what happens, in the other vertices in the second. Don't, that, let's put it with this way, you might be able to work through the construction here, but the theorem doesn't give it to you. So the theorem is only about taking a joint in the empty graph on 2 vertices for the regular graph. And have these non-zero things. Okay, now, I mean, here, this is an example where it's simple enough, you can probably work it out. Right, you can probably work it out directly, whether there is or is not perfect state transfer. My strong suspicion is that there is not.
So what's it?
Yes, exactly, right? The other ones over here, the guys that come from here, they're not going to have state transfer between, with any other vertex. I have collected, so the guys down here, those are twins, right? The vertices that have all only the same neighbors. It turns out that if I have a vertex that belongs to a set of 3 or more twins, cannot be associated with someone.
So if I
That would work, okay, so if I take O2 joined with O2, that would work. Yep, but we've already met O2 join O2, it's C4. Right, and it happens to work out nicely for C4. Great construction, right? Yeah, so there's plenty of more unknown about works than what is known about what works. So if you have an interest in construction, by all means, you should try and do it.
Hi, everyone. We have small announcement. Today at UPS we have validating program in the sales room, followed by certificate issue. So there is no lecture in the offline session. So as you are going to be.
Yes, sir, you got
நீங்க மூளைக்கு வச்சீங்களா சார்
Take up the icon.
Yeah.
Yeah, I don't understand this physics. What I just need is for somebody who doesn't understand. They or they good. If you take to me, that's a standard change. It's still be the most significant fact, but. But my sister was there because you're right, yes. I see you in person. They said. Okay. Everybody's supposed to eat now. Well, that's great, but these Europeans. We start to make legal funds. Great. Oh, that's good. Yeah. Yeah, I'm gonna talk a little bit about last. Yeah, not a lot, just a little. Okay. Let's go after my brother. Yeah, let's see. Oh,
I also don't go outside for it.
But have you heard that YouTube is not clarity? You all know YouTube video, no? It's not clarity. That's very expected in so that I will listen after that I will learn. So even I look at that one. Also, the voice is clear, right? What do you want? That video, whatever that I did on the phone. Here and now is up to 7 weeks. No, not 7. It's after the session will come with me and then we'll have this extra. Okay. So this one, or afterwards, after the verification session, and then we'll get. Okay, after certificates, application, then we will take that is going. It means the only matter department, otherwise all department. This one, yeah. That is separated, maybe. And if I think in one, so nice. So in next, so. I can. And the favorite is everyone. Okay, we will see. Where is it? All the class, that's the difference we calculation. Will be also calculated. Past plus it is also, maybe some. Hello. Because otherwise, have you seen that it's not pretty long? It makes me know you're always. I go now, na. I mean, I guess I got. And the silent.
Welcome back. Everybody ready? Alright. So, I'm gonna change tactics on you a little bit, on this one. This is, so this talk is less in the way of introduction, more in the way of, research results. And, but I'll cover off a couple of different topics with, what I hope will eventually emerge as one common theme. And common theme is going to be read at times. So, so I'll start, some of this is on joint work that I did with my postdoc, Mr. Bergman. And some of it is some results of other people who will tell you about. Okay, so we'll start out the same way that we did before. We're going to think about Moses' model for quantum communication. So it's the same idea that we had before. We have this quantum wire. We like to transfer information from one spot to the other. Think of the objective of having a data bus, a quantum data bus inside of a quantum computer, transferring the information from one spot to the other. The setup is as we saw before. We'll have an undirected graph on n vertices. Vertices represent spins, and spins that interact with each other to entangle it. Those are going to be connected by an edge. I want to select a sender vertex S and receiver vertex R. We're putting our quantum state input at vertex S. Today, we engineer physical couplings between the spins so that they interact with each other, and after time t is elapsed, read out, and we hope that the state has been communicated to vertex R, and we hope that it's close to. Okay, so this is what I told you about earlier this morning. The same sort of idea. The fidelity, I've given you the formula for the fidelity in terms of that U of T matrix that we talked about, but I'll just remind you. It's a number between 0 and 1. And so at time t, after t measures similarity between sending state, the state was sent and the state was received. After t equals 1 is exact communication of the quantum state. After t goes to 0 is poor. Okay. The dynamics are described by the continuous time quantum walk, the graph quantum network, as we saw earlier. And so the setup is just what we had before. We have our adjacency matrix A. The fidelity at time t is, so I'm using the X notation here, the matrix exponential I times T times A, I look at the SR position, and look at its complex modulus squared, that's the theorem. So this guy here is unitary. The sums of the squares of the moduli in any row are sum equal to 1, and so this guy here, this expression, the SJ entry of the exponential of IGA modulus squared, we can think of as that time dependent probability distribution, and that's the quantum quantity. Okay. And so the probability that we start by inputting a state at vertex S, and it arrives at vertex R at time t, as this the validator described here. Okay. And so I want to talk about the simplest possible case. And in some sense, the most natural thing to think about in view of the fact that the model of quantum communication proposed by those is described in the light. Okay, and so I want to talk about unweighted paths. Okay, so that's paths on n vertices where each vertex is adjacent to the one next to it, and there are no edges. And specifically, I want to think about, in this case of an unweighted path, I want to think about sending quantum information from one end vertex of the path to the other end vertex of the path. Okay? The idea here is that the distance between the two vertices that we're sending quantum information, the graph theoretic distance is a proxy for the physical distance between the corresponding spins, and so we would like to have that be long, like to be able to send our information accurately over long distance. All right, so what's the best possible thing that can happen? Right, there's perfect state transfer from one vertex to another at time t naught. If the fidelity at time t naught is equal to 1. And so here's a result of Cristiano Dutta, Eckert, and Landau from 20 years ago. So there's perfect state transfer between the n vertices of the path, if and only if the number of vertices is 2 or 3. Now, those are the two examples that we looked at earlier this morning. We looked at P2, P3. We saw that there was perfect state transfer in both of those cases. I gave you a little thought experiment about P4, right? We looked at the eigenvalues and eigenvectors for P4, and I challenged you to come up with some argument to convince yourself that it's not possible to have perfect state transfer between n vertices of P4. But what we're seeing here with this result of Cristiano and all is actually the situation is somehow worse. The only paths that perfect state transfer from one n vertex to the other are the short ones, as 2 and 3. So that's what that is. Okay, so it's a bit disappointing, but on the other hand, Modi was your 9 minutes of my lecture earlier, and I think what you will find out is that this is a field that is full of disappointments, I guess. Yes, we're good. Thank you. So this is an example of a field where there are plenty of things that we wish were true that are not. And so let me back out of the best case scenario, since it seems not to be particularly rewarding, and I want to think about what I would call a second best case scenario. Okay, so here's what I want to do. I want to stay with the paths, but I want to relax what I'm asking for out of the state transfer properties. So here's a definition that's in the literature. There's pretty good state transfer, sometimes called almost perfect state transfer, from one vertex to another. If there's a sequence of times, t sub k, so that if I look at the fidelity of that sequence of times, the fidelity converges to one, as k goes to infinity. Right? So what is this? So this is not necessarily asking for the fidelity to be exactly equal to one, but I think of some tolerance epsilon, and I say I would like the fidelity to be at least as large as one minus epsilon. And what we're saying here is, when there's pretty good state transfer, there is a time you can pick so that your fidelity will be at least this one minus epsilon. Okay, so that's sort of a second best notion. And so again, that's a question that's been addressed in the past. So there's pretty good state transfer between the n vertices of a path on, between the ended vertices of a path on n vertices, exactly in the case that n plus 1 falls into one of three categories. Either n plus 1 is the prime number, or it's 2 times the prime number, or it's a power of 2. Okay. And so I'll say that's, to me, that's good news and bad news. So this is not a frowny face, but it's also not a smiley face either. And why do I say that? Okay, on the one hand, we have an infinite family of paths that have this pretty good state transfer from one endpoint to the other, so that's good. On the other hand, I mean, it's this weird numbering theoretic thing, primes of 2 times primes, powers of 2. Who knows what that's all about? And then the other thing I want to say is that there's something a little bit frightening here about the definition of pretty good state transfer. So what are we asking for? We're asking for there to be a sequence of times so that the fidelity evaluated at that sequence of times approaches 1. Okay, so let's think about what would happen. Imagine that sequence of times were bounded. Okay, well, you do a little congruity argument to say, if that sequence of times is bounded, then in fact you can find a particular time where the fidelity is actually equal to 1, and then you've got perfect state transfer. Okay, but we already know that to be rare. Right? And for paths, it's impossible for a path on more than 4 vertices. So the conclusion from that is this sequence of times must be unbounded in K. Right? So there's a bit of a tension here between what we're asking for in terms of the accuracy of the state transfer, in other words, the fidelity being close to 1, and the length of time we're prepared to wait to get that good readout time close to 1.
Well, if this state is bounded in like this,
Yes, if it were bounded, I mean, it's just a limiting argument, right? Imagine if TKs are bounded, then what is it? There's a limit point, right? Well, then a Weierstrass theorem tells you that somewhere in there is a subsequence that converges to some particular value called tau, and then you use a congruity argument to say, well, that tau must be equal to 1. All right, so that's great if the times were bounded, but we already know that if we're dealing with 4 or more vertices, can't have perfect state transfer. It means the times are unbounded, which means we have to wait a really long time, possibly for our readout time, in order to get that good fidelity we're looking at. So just saying that in addition to the restrictions, these number theoretic restrictions on the number n, the number of vertices, there's also kind of lurking in the background here these unboundedly long readout times that we have to wait. And I'm going to come back to this readout time repeatedly through the rest of the talk. Okay, so So I'll go back to a paper of Kempton and Yao from several years ago. And so they're trying to sort of they're trying to save the past somehow in terms of state transfer, right? They're trying to come up with notions of something that's like a path that's manipulated a little bit so that we can get a good result. And so their idea is as follows: stick with an unweighted path on n vertices, but now take a loop and add a loop, a weight W, to each of the two n vertices. Okay, so that has desirable properties in the sense that the graph that comes out of it is still sparse. If that's a good idea, their graphs is sparse because every edge in our graph is something that we actually have to engineer in the lab to make the Cohen spin network work. And so what they showed is if n is at least 4, perfect state transfer from one end vertex to the other is not possible, but if the W is transcendental, then for each n at least 2, there's pretty good state transfer from one end vertex to the other. Okay, so what's the value here? The result I gave you before, the one about the prime twice prime power of 2, that business, there were no loops at the endpoints. Okay, and the message there is if there are no loops on the endpoints, then the n value has to be really special to have almost perfect state transfer. This variant here, they're allowing for loops, just 2 loops of the same size at the end vertices, and then for any choice of the length of the path, you can engineer a loop weight as long as it's transcendental. Get this pretty good state transfer. So they're able to work with any number of vertices with the proviso that they're adding loops. Okay. And so that's good, right? So in particular, there's a dense set of W values, the transcendental numbers, for which this pretty good state transfer occurs between the vertices. Okay, so that's a little bit of good news. However, in some work that I did with my postdoc Christopher, we showed when n is equal to 4, so we're talking about a path on 4 vertices, it's also the case that for any positive value of W, there's a sequence W sub k, so that the WKs converge to W, and when the loop weight is WK, the pretty good state transfer between the n vertices fails. Okay. And in fact, we showed even more, when n's at least 3, there's a set of values for W that is dense to the interval between, the half-open interval between 1 and infinity, for which we just see pretty good state transfer also fails between the states. Okay. So, what do these two things mean together? If you look at the working with paths with loops at the end vertices, that there's a dense set of choices of W that's going to work out great. There's also a dense set of W values that's not going to work out great. Okay, and so the selection of the loop weight that you have has to be absolutely precisely carefully chosen. Okay. Right. And so I want to change the objective a little bit, and in some sense, I'm going to take more of a practical evil. And so, in a way, this comes up in some conversations with some friendly physicists that I've had, because they ask the question, well, yeah, why do you care about pretty good state transfer? Why do you need the fidelity to be as close as possible to the number 1 as you care to specify? Because they're thinking about it in practical terms. Okay, they're building these things in the lab. The lab always comes with errors. Because you're not going to get perfection anyway. And so the challenge I've heard from some people working in this area on the physics side is, look, just give me something that works pretty well. Okay, give me something with decent fidelity, And that's something that we can hope to engineer in the lab, and it's probably about as much as we can expect out of this experiment. So I want to stick with the same idea. I want to consider a path on n vertices. I want to put a loop weight W at each of those two n vertices. And I want to find choices of W and n so that I can guarantee what I hope is a decent lower bound on the fidelity. And I want to tell you also, if we're lucky, which values of t will get us close to those, will get us those decent values of fidelity. And so that's the objective. Take a path, find the loop W, and in addition, also find a good readout time so that the fidelity is something reasonable. That's the goal. Okay. So let's get started here. So what have I done here? N equals 10. So I've got a path on 10 vertices. Okay, I chose value W is equal to 2. Okay, that was my good choice. And I looked at values of t between 0 and 50. And now I plot the fidelity from one end vertex to the other for this graph for t between 0 and 50. Okay, so let's take a look at that. All right, I don't know how you feel. I am disappointed. Okay, I'm disappointed for two reasons. Number one, okay, what's going on with this graph? Like, there's no pattern there to be deduced that I can reasonably see. I can't tell, you know, like, are these peaks repeating somehow or whatever. So that's one thing. I don't like the aesthetics of the graph at all. But here's what it really. Look at what the peak value is. Okay, 0.06. So there's no way you can consider this to be any way decent fidelity, at least for this group. Okay, now I'm going to show you another graph. And what I'm going to do is I'm going to zoom out. So we're going to keep the same parameters. I'll keep the same value of n, 10. I'll keep the same value of f2, but I'm going to look over a much larger interval for the t values, and we're going to see what we can. That's what we can. Okay, so I did promise much larger, so that now the t values of t are between running between 0 and 2,800 something or other. Okay, but now I feel like I'm seeing two good things here. Okay, number one, okay, it's noisy, I'll give you that, but this part, I kind of like this, okay? Because this looks like a pattern I might be able to do something with, right? And moreover, take a look at the peak values over here, so this guy and this guy. So they're running around fidelity about 0.9, okay? And I think if I took this graph to a physicist and said, I can get you fidelity 0.9 for a path on 10 vertices with loop weight 2, they'd say, okay, let's do it. Right? So an acceptable level of fidelity, at least at peaks, and some sort of pattern here that I'm going to try and understand. Okay, so the good point, this is just Iclaa. Okay, so you take the graphs for what they're worth. So I took the adjacency matrix of the graph. Iclaa has a matrix exponential function built into it. I looked at the 110 entry. I took its modulus squared and I plotted. Okay, so you know, like you might want to take these pictures with a grain of salt. Iclaa it's an error, right? So there's going to be some errors coming into it. On the other hand, it does pretty well for graphs that are small in terms of the number of reasons. So I have some confidence that the picture that we see here is something like what's happening in action. And that's sorry.
I'm asking, this is first in And then you have to update it. But what do you do?
We can hit this.
And-
So MATLAB has a built-in matrix exponential function. So I you can do it, approximates or something like that. But I mean, I checked it another way. I also looked at the eigen decomposition. So I looked at those B matrices that we talked about an hour and a half ago. And I did the exponentials of the eigenvalues and also looked at the same thing. Right? So like I said, I mean, there's pros and cons to doing things numerically, but what I want you to take away from the picture itself is maybe there is something to be understood from this picture. Yeah. All right, and so what I want to do then is I want to kind of get into the details of what our adjacency matrix looks like. And I also want to try and figure out how we're going to come up with an analysis of the eigenvalues, eigenvectors of the matrix, because what I hope you learned from my talk earlier this morning is if you want to understand this state transfer business, you have to understand the eigenvalues and the eigenvectors of the matrix. Okay, so there's the adjacency matrix. So it's to the so as you can see, it's an unweighted path, which is why these guys are super diagonal, subdiagonal are all one. Put a loop of weight W at one spot and at the n spot. And we just to note is eigenvalues in decreasing order by lambda 2 down through lambda n. I'll just pause for a second there. In fact, it's not very hard because the matrix is tridiagonal. It's not very hard to see that all the eigenvalues have to be. And that's one of the beautiful features of tridiagonal matrices that are very useful. Okay. So what do? Well, I'm going to build the eigenvector matrix. So here's my orthogonal eigenvector matrix for A of W. And the J column is going to be associated with the J. Okay, so I'll just say the V depends, of course, it depends on the number of vertices, but it also depends on the value of W, our loop weight. And so for notational simplicity, I'm going to suppress the dependence on both W and N because the formulas become unruly. Okay, and otherwise. And so then what's the fidelity? So we're looking at the 1n entry. And it's not very hard to show that the fidelity is this expression here. So it's a sum L equals 1, J equals what do we have here? L equals 1 to n, sorry, this should be minus 1. The sum on J equals 1 to n, excuse me, not that. So there's an alternating part here, okay, alternating signs with the different values of J. I look at B1J squared entry, so that's the first entry in the J column squared, and E to the IT lambda J, modulus of that squared. So that's the fidelity of straight state transfer from one end vertex to the other. Okay. So I'll just say the fact that the eigenvalues are distinct in this example means that the E matrices are just the outer products of one eigenvector itself. And so you have a slightly more direct formula here when you're looking at the expression. Okay. And so for the sake of the exposition, I'm going to talk about asymptotic ideas only. And I'm also going to suppress a lot of the formulas that come up here that the stuff that's in the paper is unreadable. I'm going to try and pre-digest a lot of the content for you so that it can capture the paper. Okay, and when I say asymptotic, I'm thinking, eventually I will be thinking of W as being large, but also possibly N as also being large. I'll try to flag those conditions when given. Okay, so we need to know two things in order to understand all this. We need to know about eigenvalues, we need to know about the eigenvectors. Okay, so let's begin. So for the eigenvalues, it's not very hard to show that the lambda one and the lambda two are respectively bounded below and above by this expression here, W plus one over W. Right? So lambda one's bounded below by W plus one over W, and two is bounded above by that same expression. You can do a little bit more, and what you can find out is that for a fixed value of W, you can write lambda one and lambda two as this guy here, the W plus one over W, plus a term that looks like little o of one over a. Okay, so as n goes to infinity, that step goes to zero. So these lambda one, the values lambda one and lambda two are almost equal to each other. Okay. Maybe a little bit surprising if you remember Frobenius theory. Okay, so remember Frobenius theory says if I have an entry-wise non-negative matrix, the biggest eigenvalue, that's lambda one in our case, has multiplicity one, nobody else can match it. Okay, that is still true in this example, but what we're seeing here is, all right, lambda two can't be equal to lambda one, but it can be extremely close to it. That's something that you usually don't teach in that and Frobenius theory, but in these extreme examples. Okay, so somehow we have a good grip on what's happening with the top two eigenvalues, lambda one and lambda two. We need to think about the other ones because they're also part of this expression for the fidelity, right? They're part of the picture. And so what you can say is that for the smaller eigenvalues, lambda 3 through lambda n, for each of those guys, there's an angle, theta j, in between pi times j minus 2 on n minus 1, and pi times j over n plus 1, so that the lambda j is 2 times the cosine theta j. All right? And in particular, it turns out that the value of this theta j only depends on the value of W. Influence of n is not present for these values. And I'll just say, if you've ever looked at the tridiagonal matrix corresponding to the adjacency of a matrix of a path with no loops, that this kind of thing here, 2 times the cosine of something or other, that's a familiar construction for you if you've seen this. Okay. So, and observe, so I want to try and point out 2 things here. So these lambda 3 through lambda n, okay, so observe that they're all bounded, right? Doesn't matter what the value of W is, doesn't matter what the value of n is, those small eigenvalues are somewhere in between 2 and -2. Okay? And on the other hand, the lambda 1 and the lambda 2 for large values of W, they're going to be large. Okay? My point here is when W is large, the influence of lambda 1 and lambda 2 is large. The influence of the remaining eigenvalues is small. Okay, so we also have to look at the eigenvector entries. And so, again, we can go through the computations. The first entry in the eigenvector corresponding to lambda 1 squared looks like W squared minus 1 on 2W squared plus something as small and as large. And the same is true for the first entry in the eigenvector corresponding to lambda 2. Okay. And so then what that means is if I take a look at the sum of the squares of the entries in the eigenvectors corresponding to lambda 3 up to lambda n, that's going to be something like 1 over W squared plus stuff that goes to 0 as it goes to. Okay. So think about large values of W here. I think that might be helpful. What we're saying is when W is large, the entries in the first position correspond, the eigenvectors corresponding to lambda one and lambda two, those entries are roughly 1/√2 each. Okay, and the rest of the stuff, the rest of the mass of those eigenvectors for the other eigenvalues is small. Okay. So, how do we come up with all of this stuff? So the estimates for the lambda one and the lambda two come out of the fact that they are the largest eigenvalues of these two matrices. Okay, so this one and this one, in case the n is even and is odd, they are the largest eigenvalues of these two matrices. And they're very similar to each other. What they look like are, it's in broad terms, it's the adjacency matrix of a path of roughly half the length. We still have the loop in the first vertex of the path, and then there's some little correction thing that we put down here in the bottom right hand. And then it turns out that the corresponding eigenvectors for these matrices are positive, and they have some nice curves for which that I know. Okay. So that's sort of telling a bit of the story for the eigenvectors. For the eigenvalues. Now I want to tell you a little bit about the eigenvectors. So I want to build this matrix here. Okay, it's built of signs appropriately normalized, and in addition, I'll have a corresponding diagonal matrix built out of cosines. Again, if you've ever worked with the eigenvalues of the path matrix and the eigenvectors of the path matrix, these are going to be familiar functions to you. If I build a matrix like that, then it turns out that Q times D times Q transpose is the adjacency matrix of the path on the minus two vertices, and our adjacency matrix with the loops added at the first and last vertex can be written this way. Okay, and so then a lambda one eigenvector can be written like this. So I'm capturing out the first and last entries of the eigenvector. I'm giving a name to the stuff in the middle. Here's the normalization factor here, and the U is Q times lambda one minus the inverse Q transpose times the sum of the entry that had the sum of the vector that has the one in the first position and n minus two in the last position and zeros everywhere else. Okay, so it's just a bunch of stuff you have to go through in terms of the computations. And what you find out when you punch through the technical details of what this expression looks like, the U transpose U, so that's this guy down here that we're worried about, it's essentially a Riemann sum for a, I'm not even going to tell you what function it is, a not pleasant integral that you then can go ahead and evaluate. Okay, and what that means is we're then able to remember what we're trying to do here is we're trying to capture the size of the first entry, and so that's going to be 1 over square root of 2 plus this U transpose U, but the U transpose U is a Riemann sum. Okay, we're going to be able to evaluate that as an approximation for that value of U1 squared. Okay. Same sort of business for weak V1 all squared. It's same kind of construction that you see. Okay. And so let's look at an expression for the fidelity. You've seen this trick before, but I'm not doing anything more complicated than looking at triangle inequality. So the fidelity is bounded above by let's see, I'll have V1 squared, take away e to the I t lambda 2 minus lambda 1 V1 2 squared, so the modulus of that, plus the sum of the squares of the other entries in the eigenvector that corresponds to lambda 1, that whole business squared. Okay, and as long as this stuff here is greater than zero, and this is the important point, the fidelity is going to be bounded below by the same expression that I had before, take away that sum of the entries in the first eigenvector corresponding to lambda one, sums of the squares in positions 2 through. Okay. So now what do we do? I'm going to set x is equal to t times lambda one minus lambda two. And now we use our estimates on the eigenvector entries, and we find out that the fidelity is bounded above by 1 minus the cosine of x, w squared minus 1 on w squared plus 1 over w squared, plus the term that goes to 0 with n. Okay, and I can recast that whole thing like this. Right? And as long as I have the positivity assumption here that I gave you before, this is the important bit, the fidelity is bounded below by a similar type of expression, okay, which I can rewrite sine of x over 2 w squared minus 1 on w squared minus 1 over this w squared plus 7 goes to 0 with n. Okay. And so when we're all done, same sort of technique shows that if w is bigger than the square root of 2, and I take any choice of natural number k, that the fidelity evaluated as 2k plus 1 pi divided by lambda 1 minus lambda 2 is bounded below by w squared minus 2 or w squared the whole squared. Okay, that is a lot of formulas, I'm sorry. But here's what I want to focus on. It's this last inequality here. Okay, because what is that? That is a lower bound on the fidelity. It's at a particular time, okay, log multiple of pi on lambda 1 minus lambda 2. And think about it, what happens? Imagine the W is large. Okay, then the stuff on the right-hand side is almost equal to 1. Right? And so that's kind of accomplishing the objective that I was looking for. I want a pretty decent lower bound on fidelity at a particular time that I know when to evaluate that, so that I can understand that I'm getting a reasonable level of state transfer from one end vertex to the other. Okay. Let's talk a little bit about readout times. So imagine that epsilon is positive and it's been given, and let's suppose that 1 minus epsilon is bounded below by this expression. I need my loop weight to be at least the square root of 2 here. And let's suppose that we're looking at a particular time where the fidelity is bounded below by 1 minus epsilon. Okay, and what I want to do here is I want to try and figure out where is that fidelity, what are those values of t. Okay, so it turns out that if that's the case, our t has the form kind of what you expect: odd multiple of pi plus some error term tau divided by lambda 1 minus lambda 2. Okay, and what's the story on tau? Well, tau in absolute value is bounded above by the inverse cosine of this stuff here, right, plus 1 of stuff that goes to 0 with n. Okay, so in other words, if I'm looking at a value where the fidelity is at least 1 minus epsilon, the readout time must have been very close to an odd multiple of pi divided by lambda 1 minus pi. Okay, we can actually sharpen this business on readout time to come up with a slightly more detailed expression. So imagine that W is a value that yields pretty good state transfer from one end vertex to the other. And let T sub j be a sequence of readout times so that the fidelities approach 1, state j goes to infinity. Then there are there's a sequence of integers k sub j and a sequence of angles tau sub j between 0 and pi, so that the t sub j readout time is the corresponding odd multiple of pi plus our error term tau sub j divided by lambda 1 minus lambda 2, and in addition, that error terms, these tau j's, go to 0 as j goes to infinity. All right, and so what we're saying then is if the fidelity for our path with the loops dependent, if our fidelity is close to 1 at some particular time, it must have been that that lambda 1 times lambda 2, sorry, lambda 1 minus lambda 2 times our readout time must be pretty close to an odd. Okay, and in fact, I'll just say a caveat here. This is kind of, I'll come back to this in a moment. We can look a little bit at our estimates of lambda 1 and lambda 2 to find out that the difference between those two numbers is on the order of 1 over W to the n minus 2. Okay, and so what that means is these readout times here can actually be quite low. Okay. So let's take a look at it numerically. Again, these are just MATLAB computations, so just like whatever, to take it for what it's worth. But I want to kind of give you an example, at least for small values of n and w, what the fidelity of the time. Okay, so we're going to put it here. So I've got some different choices of the value of n, and so I've chosen n to be either 5 or 10, and then I've just taken some small values and dumping into 3, 4, and 5 for each of those. Observe that each of those is bigger than the square root of 2, so the hypotheses are very variable. And so in the first column here, I'm computing pi over lambda 1 minus lambda 2. In the second column here, I'm computing the fidelity at that value. Okay, in the third column, remember here's our lower bound on fidelity, so this is w squared times 2 over w squared the whole thing squared, that's our lower bound. And then I've got this T max, I'll tell you what that is. T max is the time during the interval between 0 and 2 pi on lambda 1 minus lambda 2, where the fidelity is maximized generally. And then the value at this T max. Okay. So there's a couple of things that you see. I'll try to insert this here for you. Okay, so these values of T, okay, are pretty large. Pi over lambda 1 minus lambda 2 is pretty large. And when n is 5, and they are very large on the orders of 10 to the 4, 10 to the 5, 10 to the 6. They're very large when n is 10. My values here for the fidelity evaluated at pi on lambda 1 minus lambda 2 are, well, they're not that good for w equals 3. Okay, you can say, see here, the values are not that good. But then as w increases, it seemed to improve a little bit, 0.9062 and 0.9265 for the 5 case, and 0.9131 and 0.221, 10 by 10 case. Okay, here's my lower bounds on the fidelity. Okay, and they seem to be well, they're not bad, but they're not a very good approximation for what we see here today. Right? And then the T max, well, we've seen similar sort of behavior here. T max does what we expect it to do, right? So you can see that line by line, the T max value is reasonably close to pi to lambda 1 minus lambda 2. The good news here is that at the T max, the fidelity at that maximized value, but the readout time is actually really good. Okay. So we've got some mathematical stuff going on there, but then, some numerical stuff that seems to support the case that even when the values of the W are not too big, and the values of the N are not too big, we're still getting reasonably good fidelity, with readout times that are real. Okay. So I wanna focus now on a slightly different type of result. It's very much in the flavor of what I was telling you before. And well, I'll sort of compare the result that come out of this one with what happens for the path. So now I want to forget about the past for a second. I'll look at. Yeah, so this is just this is just kind of a sampler, right? You have two different values of N and three different values of W. Just looking at the difference between what the theory tells us is the place where we should be looking at, what lower bound looks like, and then what the actual is. And I mean, the takeaway from this slide here is the performance is actually better than what the theory tells us, okay? And maybe that is not surprising. What I produced was a bunch of estimates, right? So we had some inequalities where we threw some terms away. So of course, we're not gonna do it as well as what's possible when all the terms are taken. Okay. So I now want to think about a broader family of graphs. So let's just think about a connected graph on n vertices. And maybe you met this definition before, maybe you haven't. Our graph sheet has what's called an involution. If there's a bijection from the set of vertices to itself that has two important properties. First of all, if I apply the bijection twice to a particular index j, I just produce j back again. Okay, so sigma squared of j is just j back again. And it also preserves adjacency. In other words, if j is adjacent to k in our graph G, then sigma j is adjacent to sigma k. Okay. And so then, yeah, and so why is this important? Well, let's just think, well, let me just add one more idea. I want to take a graph that has an involution. I want to select a vertex J. Let vertex K be its image under that involution J, and then I'm going to add a loop of weight W at vertex J and that its image. Okay. And why do I bring this up? Well, our path with loops at each endpoint is an example of exactly this thing. Okay, how do I do it? Okay. Imagine the path here, and I label the vertices 1, 2, 3, all the way up to n. Okay, I put a loop of weight W at vertex 1, and I put a loop of weight W at vertex n. What's the involution that I'm caring about? The involution is the map that takes the index j and sends it to index n plus 1 minus j. Okay, and what is that? All I've done is I've taken the path and written it down in the opposite order. And so in other words, our example of the path with the two loop weights is an example of a broader family of graphs, and that's these graphs that possess an image. Okay. So here's the results of Victor and Sheen from a couple of years ago. So let's take a graph that has maximum degree m, and I'm thinking of it as having been constructed in this way. Okay, so it's a graph. There's an involution. I pick a vertex and I pick its partner under the involution, and I add weights W at both of those two vertices. Okay. So here's the result they get. So they denote the maximum degree by M. And they denote the graph theoretic distance between J and K. So remember, this is the vertex we chose. Here's its image under the solution. Let's have that be d sub jk. And now let's take a tolerance epsilon that's been pre-specified. And we'll imagine that the loop weight is bounded below by this crazy thing, 256 m plus 1 on epsilon squared. Okay? Then the conclusion of the theorem is there's a time t naught, and it is in the interval between 0 and pi over 2 times w plus m raised to the distance taken away 1, so that f of t0, f of t naught, is bounded below by 1 minus epsilon. Okay. So it's roughly speaking the same sort of analysis that Littner and She do that took place for the path. Okay, they do some estimation of the largest two eigenvalues of the adjacency matrix for a graph of this type. They look at what properties the eigenvectors have, and they push through a computation in a manner not exactly the same as what I showed you for the path, but in a parallel sequence of considerations. Okay. So I'll just say, what's the advantage of this theorem? Okay, well, number one, they've got a much larger family of graphs going on here. Okay, so the result that I gave you earlier only applied to paths with loops at the endpoints. So they're able to look at a larger family of graphs, and moreover, they're able to produce, they're able to look at many pairs of these vertices that are connected by the fact that there's an involution outcome to the end. That's the advantage. The disadvantage is the issue that they come out with the read time. So, I mean, what the assertion here is that there's a T naught somewhere between 0 and whatever this monstrously large number is. Okay, some T naught to be found in this wide interval will give you this great fidelity. So that's good to know. Okay, it's good to know that there is a good choice of T naught, but we don't have a good sense. Where would we go and look to find the good value of T naught? So to me, there's trade-offs between the two results. They have a larger, much larger family of the graphs to think about. On the other hand, the results on the paths, because there's such precise information on the paths, the results on the paths give you a sharper window on the data terms. Yeah.
Regarding graphs for which it was
So that would be a great challenge, right? My sense is that to make progress on the readout time problem, you need to know more about the structure of the graph than just the fact that it has a resolution. So
there is a circle graph before paths.
So I think the result for paths is so the result of paths here is not as good as the result that I showed you earlier. The way doesn't have to look at.
But does that vary?
I believe it does, yeah. It does. So the readout time that I gave you, the higher than 1 less than 2, falls in this interval. Okay, but I believe that this interval is very much larger than actual readout time that we're asking you to look at.
Left side and the you chose and left side and the other, the correlation is same.
Yeah, so where's the value here, right? So they're looking at, yeah, so there's a square, there's an inverse square relationship between the W and the epsilon. I think that's true for the results as well. Okay. Right. So now what I want to do is change gears yet again. I want to keep the idea of readout times, good fidelity, as sort of top of mind here. But I want to give you a couple of other types of graphs to think about where we have something good to think about in terms of readout time and fidelity that is connected with state transfer between vertices. Okay, so in a different project with Christopher, we talked about a couple of different families. So these are this is a family of trees of diameter 4. Okay, so so you can see that so where's the one cut? So I go from here 1, 2, 3, 4. So if I try to go from one of the white vertices on the left hand side over to the right hand side, I have to travel a diameter. Okay. And so here's the construction. I take the odd value of k bigger than 1. So I have this central vertex here in the middle, and now I'm going to attach k squared any vertices of degree 1 to that central vertex. Okay, so that's what's happening down here. And then I'm going to have k squared minus 1 branches that look like this. So I have these two white pinion vertices adjacent to this black guy, and then the black guy adjacent to our central vertex. Okay. So that's what the trees look like. And now, why have I flagged the white vertices? I want to talk about the fidelity of state transfer between pairs of white vertices that are adjacent to the same neighbor here. Okay, so state transfer from this guy to this guy, state transfer from this guy to this guy, and so on through all of the remaining branches that are attached to that central vertex. Okay. And so I just written the whole crazy formula for you here. So I've given you a value of the readout time. Okay, so I'm saying take n odd, and now my value t naught is 1 plus root 2 raised to the nth power plus 1 minus root 2 raised to the nth power divided by 2 root 2. Okay, that whole thing multiplied by pi. Okay, let's see. I believe, let me get this right. I believe that, yeah, I can say right. So I evaluate the fidelity of this magical value of T naught. And here's what I come up with. I'll have a 1, and on the 1 over 1, sorry, 1 over 2k squared, take away 1. 1 minus the cosine of root 2 minus 1 to the n, root 2 times pi, the whole thing squared. Okay, now that's a lot of detail to unpack for you. But let me just try and think about what happens for large values. So let's see. I've got root 2 minus 1 to the n, right? As n goes to infinity, that's going to converge to 0. So this stuff in here is 1 minus the cosine of something that's going to 0. So this part is going to disappear as n goes to infinity, which means that the fidelity converges to 1 as n goes to infinity. So in particular, this is an example manifested in a really concrete way of this pretty good state transfer. Okay, I have produced a sequence of times, this guy here, such that when I evaluate the fidelity of state transfer from this one to this one, at that sequence of times, the result converges to 1.
Can I have motivation behind what you have mentioned?
Sure. Yeah, so because I don't want to leave it to be mysterious. So here's what we were looking at. We were looking at trying to understand pretty good state transfer for trees of diameter 4. Okay? So it turns out that it can only happen in a very limited number of cases, very limited number of constructions. And so what we were looking for then were, and so we were able to characterize the different cases that there is pretty good state transfer inside of trees that have under 4. But what we also wanted to do was construct examples where we could give precise values of the readout times so that the fidelity of those readout times converges to 1. Now, I don't want this to be mysterious. So I want to look at how do you come up with this stuff here. So when you look at the trees that we're talking about here, and now we have to think about, and this goes back to the considerations I had in my earlier lecture. We have to think about the eigenvalues that are in support of the vertices that we care about. Okay, now, if I remember properly, so there's an eigenvalue 0 that we care about. Okay, that's in support of those vertices. And then there's also an eigenvalues of the type square root of 2 times k and minus the square root of 2 times k. Okay? And now let's just think about that perfect state transfer characterization that I gave you in my earlier talk. We need the eigenvalues to do exactly the right things on the positive part of the support and the negative part of the support. Okay, asymptotically. All right, and so let me try and unlock the mystery here. If you look at a sequence of rational approximations to the square root of 2, okay, and in fact, this is a sequence that comes up out of considering continued fractions. Okay, so that's one of the ways we can approximate the square root of 2 by rational numbers is through a sequence of continued fractions. So remember, I've got some numerators and some denominators. If I look at this sequence of rational approximations, these T naught values, these are the denominators. Okay, and so when I look at the readout time here, then I'm going to come up with, and then we're going to have b to the I T naught times lambda, right? And so if I'm approximating T naught times lambda now will be almost equal to the numerator that goes with this guy is the corresponding rational approximation to the square root of 2. Okay. I don't want to say any more about it because you need to really understand it. You have to stare down all formulas. But the idea here is because we had good control on the eigenvalues, we could use this idea of rational approximations to the square root of 2 to tell us how to come up with the readout times. And then the rest of it, all this business here, this is just going through the algebra, writing out what the value of the dominant is. Okay. So and I absolutely realize that I am sweeping a lot under the rug when I tell you that, and you should agree. Okay, because the details are awful. All right. One more family of trees that we talked about. So again, this is an example of a family of trees of diameter 4, 1, 2, 3, 4. So this is, again, we have a central vertex here. It's got 2 branches, each adjacent to one of these white vertices. And then there's Q pendant vertices adjacent to the white vertex and to the 2 sides. Okay. And so what I look at here is the fidelity of state transfer between the 2 white vertices. Okay. Now, there's a lot of symmetry in that graph, and I bet you will believe that those 2 white vertices are strongly cospectral. Okay, in other words, for the eigenvalues of the support of, say, this left-hand guy, there's going to be this nice positive negative relationship with the corresponding eigenvalues. And so here's the result that we came up with. Again, formula heavy, but I'll try and explain what's going on here. So I've got these two parameters here, R1 built as q plus 1 plus the square root of q squared plus 2q. And R2, well, that's just part right now. It's q2, q plus 1 take away the same square root. And now I write d sub k in this fashion here. So it's R1 to the 2k, 2q plus 1 minus R2 times R1 minus 1 taken away. And then I have a parallel expression here where I'm exchanging off the rules of R1 and R2. And then the whole thing is divided by twice R1 minus R2. Okay. And so then I'm going to take T sub k as this guy here, tk times pi divided by the square root of q. And I'm going to take this guy here, delta sub k, that's R2 to the 2k, R2 minus 1 on 2 times the square root of q plus 2 over q, take over 1. Okay. Again, it's quite a bit of algebra to absorb, but I'll try and explain why it all comes out that way. So the fidelity at our time t sub k is 1 plus the cos of delta k pi on 2 all squared. Okay, so let's take a look at this delta k. The behavior of delta k is some horrible constant, this stuff here, R2 to the 2k. What's R2? Let's take a look at that expression there. That is some number that is between 0 and 1. Okay, so now power and not R2 to the 2k power, this delta k is going to converge to 0. This k goes to infinity, right? And so then cos of delta k plus 1 is going to converge to 1, which means the fidelity converges to 1. K goes to infinity. Okay, so the point here is we have an extremely specialized construction here. Whoops, this guy here. Very specialized construction for a tree of diameter 4. The plus side, I mean the positive side of it is we're able to identify a concrete sequence of readout times where the fidelity converges to 1. Okay, so my last thing is to try and explain where this choice of TK comes up. Well, one of the things that we need to worry about is being able to estimate the square root of q plus 2 on q, right? Because that's one of the eigenvalues that we have to care about when we're looking at support of those two white persons. All right, what is this? Okay, well, this is the same sort of animal that I gave you before. This is the denominator of a sequence of rational numbers that approaches square root of q plus 2 on q as k goes to infinity, right? And that denominator, it's exactly that. It's the same technique that I told you about before. You look at the continued fraction expression for a root of q plus 2 on q. You pick out the numerators and the denominators, and there you go. Okay. And so, so what I will say here is, again, advantages and disadvantages. So advantages to these two constructions that I gave you for the trees is we get a concrete sequence of readout times and a concrete sequence of fidelity values that we can work with. I would say that the disadvantage in both of those examples is the low diameter situation. Okay, so the first tree we talked about vertices that were distance 2 from each other, and second one were those two vertices where we're doing state transfer between also had distance 2. Okay, and so as I said before, the ideal is to come up with large diameters for our state transfer, and this is not a good thing at that time. Okay. I will say that one of the reasons why this works out and we can come up with these explicit computations, explicit expressions in both cases, is because we're talking about small number of eigenvalues that we have to care about. Right, the supports of the of the vertices that we care about in both cases, the supports are small in cardinality, which means we only have to estimate something simple through rational approximation. That's really what it can support. What we find out is when we start dealing with eigenvalue supports for a particular vertex that have lots of eigenvalues in them, the estimation problems are very much higher. Okay. So I think I will wrap it up here. To just try and capture what was going on in the results. So for the path of loops, we saw from that picture that I gave you that we have this sort of noisy periodic behavior for the deltas between the vertices. And what is that? Well, the fidelity bands that we were looking at look like this, okay? So they look like there was a lower bound where we took the -1/W², the upper bound where we would have had a +1/W², and then the x value here was t times lambda 1 minus lambda 2. So if you thought about those two curves and something that interpolated between them, you would get that kind of noisy periodic behavior that we saw in the picture. Okay, so I showed you that chart for numerical values. And I would say that at least for the values of the deltas that we were thinking about, I think it was 3, 4, and 5, the lower bounds on the fidelity were compared to the actual values at pi lambda 1 minus lambda 2, they were kind of pessimistic. And I'll just say that the expressions that I gave you are in fact more involved than what I showed you. So here's an example of that exact expression for B11 squared. So it's the reciprocal of 2 plus, and now I'll just remind you what I said earlier, right? So we had this thing that looked like a Riemann sum for an awful function, and you can kind of see it over here, right? Here's a 1 over n minus 1, sine L equals 1 to roughly n over 2. I've got sine squared of something or other over lambda 1 minus 2 something or other squared, and that is a Riemann sum, some unpleasant function. Okay. So what we saw is that the pass was loops, graphs with an involution, and our diameter tree examples, all the news is mixed. Okay, we have the guaranteed lower bounds on the fidelity. But what we saw in all of those cases is the readout time is blowing up as you ask for better and better fidelity. And that's kind of what you expect. As I said earlier, if we have pretty good state transfer from one vertex to another, necessarily the readout times are unbounded. So you should expect them to be large if you're asking for values of delta universe. Okay, I'm going to stop there and I'll thank you for your attention this morning. You also have to take a question now.
We take wrongly directed. We can reach out from every vertex to another. But we cannot use spectral here.
Right.
What else? Which you want to know?
Okay, so I'll just rephrase the question so everybody can hear. Essentially, the question is, what can you do with a directed graph that is strongly connected? Okay, completely natural question. And the challenges you've already observed is that beautiful expression in terms of the eigenprojection matrices and all of that stuff, hopefully, okay, no hope. And moreover, I would say it's not clear even that if I just took the adjacency matrix of my directed graph, it's not clear what properties that e to the ITA as. Okay,
Which was in the, class in his, in that.
well, so I mean, essentially, the thing I'm gonna propose is something that captures the adjacency of the matrix of the directed graph. The idea is, how does it work? So you know about, gee, I don't remember what the terminology is. The point is you want to try and develop a Hermitian version of the adjacency matrix for a directed graph. And so the kinds of things that people have considered are like this. So I pick a pair of vertices, right? So, okay, easy case. There's no arc either way. Okay, so then don't do anything, just put zeros in the matrix, right? Okay. Second easiest case, there's an arc one way, and there's an arc the other way. Okay, so let's just put a line in the ij position and a one in the ji position. Okay. Third case is imagine there's an arc one way, not the other. Okay, so the proposal for this is take take a weight of I, square root of -1, for to go from say vertex j to vertex k. All right, and minus I to go the opposing octadiagonal position. Okay, so that leaves you with a Hermitian matrix. Okay, it captures all of the information that you want in the sense that it knows the directed graph. It knows when there are no arcs. It knows that when there is an arc going both ways. And there it knows when there's an arc one way and not the other, and which way the arc, because that's where the I is, as opposed to the minus I. Okay, and so then the proposal is start with that as, I think it's called like a mixed adjacency matrix or something like that. Start with that as your version of an adjacency matrix, and now work with that. Okay. The good news is, so I have a spectral theorem for that because it's a Hermitian matrix. You're still going to get our U matrix is going to have all the properties that we wanted. It's going to be unitary, so I can have this notion of the modulus squared of the entry is representing the probability of statements, but etc. etc. So there's definitely some work in looking at those kinds of problems. Now, I will say that the question mark around this is whether it's implementable in the lab. Okay, I think that the zeros and ones, I have no problem figuring out how to do that in a laboratory if they have a particular directive course to work. The question is how you realize the one way mark. Now I've had it said to me that as mathematicians, that is not our problem. Okay, as mathematicians, we should come up with whatever good structure we can concoct in our minds, and then it's up to physicists to build that. Okay, I even heard that once from a physicist. I don't know whether he was quite a bright mind at that time, but I'm just saying it's a great question, and it's not clear. It's not clear how to proceed with it in a way where there's enough mathematical technology to make the analysis tractable, and in a way that's also realistically implementable in the setting. You raised the Laplacian matrix. I'll just say, in line with that, think of any matrix you like and then make the physicist build it. So there is all kinds of work dealing with other matrices that understand the graph. So there's definitely work with the adjacency matrix, which I told you about earlier, with the Laplacian matrix, with what's called a normalized Laplacian matrix, and also the signing Laplacian matrix. So those are all examples of matrices that we work with in spectral graph theory, where we have good understanding about the properties, and consequently the technique that's developed for those matrices can also be adapted to state transfer models. Okay, anything further? All right. If not, thanks for your attention. I don't know what you want to do to be tried. So the issue here is. Trying to find some- Perhaps. Yes, I do. And so, yeah, so it's. Yeah, so the problem is, as a, the graph theoretically is very small, right? It's just taking around to something. Yeah, so the problem is getting more complicated. Now, still can have some nice things that you got this clear symmetry. Even, I mean, you could even take it much stronger and then take a bunch of pain versus on one side. That is an example of that in evolution, so some of the techniques that are in that evolution paper. Okay. So, I mean, what happens is that as a result, it goes like this. So if I have vertices at distance E, and I'm going to imagine this from which I would have to be doing and I think it's the case that the support, I think now the support those verticals are now these running. I think that's the so what that means is, so we wanted to do state transfer over long distances. Okay, that's this is how it can be physically setting. Trade-off is I think the obviously have to look at as large as one would do. My experience is dealing with a lot of other values. That's something is constantly everyone. So that's part of that reason why we're designing streets which I report. So we're looking at small level group, so we like big supports. Maybe you get about the initial. Sure, we can do. Yeah, I'm sure. Yeah. Yeah, and so this has been complete with also the CHIM, and they deal with state transfer programs, troops, security general. So they look at those things, and it's actually because of like if you want to get started, it's not about most of the at all the techniques available, rather so it makes the structure so all of those. Yeah. No plan, but you never know when it's there. Yeah, so I'm part of this program, which I'm one months, Billy's just some topics. But yeah, I haven't moved to the area and right now. Not actually.
I have some more of that done.
Yes.
So that's so you would have contracts.
Yeah, and here it was, there was. Yeah, I mean, absolutely, yeah, yeah, the largest one. Yeah.
No. No.